All right, welcome to the Explainer. You know all those incredible AI tools we're using every day? Well, today we're going to look at the absolute monsters of engineering that actually power them. We're going beyond the software, diving deep into the silicon, the transistors, and the truly radical designs that make it all possible.
So let's just start with a number, 4 trillion. Now that's not a government budget, it's not the number of stars in a galaxy. That is the number of transistors that can be packed onto a single piece of silicon. Yeah, a single computer chip. It's a number that's almost impossible to wrap your head around. And that just leads to the obvious question, right? What on earth could possibly need that kind of power? Well, the answer is those massive, world-changing AI models that have kind of become part of our daily lives. See, to really get the hardware, you first have to understand the sheer, mind-boggling scale of the problem it's trying to solve.
Okay, so let's get right into it. The heart of the problem, really, is that these modern AI models, they have an absolutely endless appetite for memory and for computation. We're talking about a scale that just dwarfs almost anything we've ever seen before.
So let's take a model like GPT-3, for example. It's built on something called parameters. Now, you can think of parameters as, well, they're like the learned knowledge of the AI. They're all the tiny little adjustments it makes as it learns from tons and tons of data. And the rule of thumb is, more parameters usually means a more capable, a smarter model. But when you have 175 billion of them, it also means the model is just gigantic.
But, it's not just about how many parameters you have. It's also about how you store them. And this concept is called precision. It's kind of like this. Imagine choosing between a simple ruler that only measures in whole inches. That's low precision, right? It saves space. Or you could use a super precise digital caliper that measures to 1,000th of an inch. That's high precision. It's way more accurate, but writing down each one of those measurements takes up a lot more room. And this is where the scale of the challenge just smacks you in the face. Look at this. At high precision, that's FP32, our 175 billion parameter model needs 700 gigabytes of memory just to load, just to exist. Okay, let's cut the precision in half to FP16. You still need 350 gigabytes. Now, think about your high-end gaming PC at home. It might have, 16, maybe 32 gigs of RAM? We are in a completely different universe of scale here. It's not even close.
So, faced with this insane demand for power, where did the industry turn? Well, they turned to an old friend from the world of computer graphics, but one that was about to get supercharged for a whole new era. The graphics processing unit, the GPU.
Okay, now, it is absolutely crucial to get this. The GPU in an AI data center is a completely different beast from the one in your gaming PC. I mean, sure, a gaming GPU like an RTX 3080, it's a powerhouse, no doubt about it. But the NVIDIA A100, a data center GPU, it's just on another level entirely. We're talking nearly double the transistors, way more high bandwidth memory, and specialized hardware built for one single purpose: crunching AI math. And the real secret sauce inside these monster GPUs is something called tensor cores. So if you think of the whole GPU as a factory, the tensor cores are like these specialist workers on the assembly line. They are perfectly designed to do one job and one job only: the complex matrix math that's at the very heart of AI. And they do it at absolutely incredible speed. These things really are the engine of the AI revolution. But here's the catch. Remember our 350 gigabyte model? Well, even this top-of-the-line A100 GPU with its 80 gigs of memory, it can't hold it. It's not even close. The engine, as powerful as it is still too small for the giant vehicle it's trying to power. So what's the logical next step? Just use more engines, right? Well, as it turns out, simply wiring a bunch of these powerful GPUs together creates a brand new and really serious problem. You might solve the memory issue, sure, but you create a communication traffic jam of truly epic proportions. I want you to imagine a team of brilliant engineers, each at their own workbench. They're all working on the same huge project, right? But the blueprints and parts are split between them. So to get anything done, they constantly have to walk down this one single narrow hallway to share tools and pass parts back and forth. You see the problem? No matter how fast each individual person works, the entire project slows down to the speed of that hallway. That's exactly what the multi-GPU bottleneck is. The data moving between the chips becomes the ultimate speed limit. And look, this isn't just some theoretical problem I made up. It's got a technical name. It's called NUMA effects. But it's exactly what we just described, a memory traffic jam. And as this research paper points out, it's one of the primary bottlenecks for performance when you try to scale out with multiple GPUs. Plain and simple, the hallway just isn't wide enough.
So this all leads to a really radical question. What if? What if you could just get rid of the hallway entirely? What if all the engineers, all the tools, all the parts, what if they were all on one single gigantic workbench? And this is where we see a truly revolutionary leap in hardware design. Instead of trying to connect dozens of smaller chips, some companies decided, you know what, let's just build one single, impossibly massive chip. This, my friends, is the wafer-scale revolution. This really brings us to two competing philosophies. On one hand, you have scale out. That's what we've been talking about, linking lots of powerful individual chips together. But the new radical approach is scale up, building one single monolithic chip so large it covers an entire silicon wafer. The crucial difference? It's all about communication. On a wafer-scale chip, data just moves across the silicon itself, which is literally thousands of times faster than sending it across wires to a whole different chip. The bottleneck? It's just gone. And the result? Well, it's a completely new scale of computing. I mean, just look at these numbers. The Cerebrus WSE3 has 4 trillion transistors. 4 trillion, compared to 80 billion on NVIDIA's latest H100. It has 900,000 AI-optimized cores. And get this, its on-chip memory and interconnect speed, we're talking 44 gigabytes of memory on the chip itself with an internal communication speed of 21 petabytes per second. That is what it means to put everything on one giant workbench. Yeah, and seeing it visually like this really drives the point home, doesn't it? I mean, the bars for the H100 and Tesla's Dojo chip are super impressive on their own. But then you look at the Cerebrus WSE3, and it's just on another planet. It's not a chip. It's a whole city of compute cores built on a single piece of silicon. Okay, so we've looked at all this incredible tech. But why does this hardware race actually matter? I mean, for you and me, what does it all mean? This is the big takeaway, right here. This isn't just some academic exercise to build a slightly better chatbot. This level of raw computational power, it unlocks the ability to tackle some of humanity's most complex and pressing problems. We're talking about things like discovering new life-saving drugs, creating climate models that are actually accurate, or designing brand new materials from the atom up. So what we're really seeing is this incredibly powerful feedback loop. It goes like this. AI researchers dream up bigger, more capable models, which demands more powerful hardware. So the hardware companies innovate in these crazy ways. But then, as soon as that new, more powerful hardware exists, it lets the researchers dream up even bigger models. The cycle just repeats, and it accelerates progress itself. At the end of the day, we are building machines with a capacity for computation that is just truly unprecedented. The hardware is here, so the challenge for us is no longer about if we can solve these massive, complex problems. It's about deciding which ones we should point this incredible power at first. Thanks for watching The Explainer.